Thank you, John. Thank you very much, and thank you, friends of Imperial, for this opportunity. So here I am. I'm Guillermo. You hear the nice introduction there. Thank you for the nice words. So today I'm going to be talking about fire science, and also how it relates to fire engineering. And I'm going to be talking both about fire in buildings and fires in the forest. So you can see in the presentation here, you can see in the presentation here, that's the Great Fire of London in 1666. I am speaking to you from London, where I work, where my family is, and my kids are Londoners. It's a big event that shaped a lot of the built environment in the city and abroad. And pretty much every single city around the world that is a couple of 100 years old has had an equivalent Great Fire of London. It's just that London and the UK are very good at conserving and learning from history, but every city has had a fire where they could learn from if they were interested. Modern fires in the city more likely are like this. This is a very famous experiment conducted at BRE, also in London, where is a living room. This was from the 70s, a living room, but still modern in context. And these are the fires that really worry us, the ones that actually lead to losses of life and losses of property when our living rooms are burning. However, in context, if we look back over the last many decades, we can see that fire safety, thanks to fire engineering in a significant amount, has been improving. What you are seeing in the plot over here is since 1982 until current date, how the fatalities, the fire fatalities in the UK have been consistently being reduced, and it has dropped by 60% over the course of 3.5 decades, which is a massive and very strong signal of success. If you were to look into worldwide data, the only other country that has a decent amount of fire statistics is the United States. So both the UK and the US have the best databases in time and quality. And they also show you that over the last 100 years, 90% of the fire deaths in the US have been reduced. So it's massive success for fire safety engineering. We continue being worried about fire safety engineering, about fire, but imagine how it was 100 or 30 years ago. So this is US and the UK. They are well-developed nations, powerful leading nations. But if we look into what happens all around the world, what we see is that fire is a horrible disaster that we have in every single city. It causes about 5% of the deaths, accidental death, caused due to casualties, caused to an injury, sorry. Compare that to 2% of the deaths, accidental deaths, are produced by war. 2% of the deaths caused by injury. So that's excluding, obviously, the ones that are because of health reasons. So 5% of the fire death is all around the world. It's a massive, I'll take this away. It's a massive number. Also for the UK, although there is this big success reducing by 60% in 3 decades and a half, well, the cost for the country is significant. The cost in terms of money, in the indirect and direct cost of the UK is about 10 billion per year. And 10 billion per year is a significant amount of the money of the nation going into protection. And citizens demand even more and better protection. The context of fire safety engineering is that the built environment, the way our buildings are. So the context of fire safety engineering is that fire safety is actually always changing because citizens, technology, and architects keep thinking of new ways of building, of doing buildings. There is a quote here that I said once that was mentioned in the community before, is that the architect's dreams can be the nightmares of fire engineers. I'm not being pejorative. I really like architects and their dreams, and they keep our buildings beautiful and interesting and attractive. But fire engineers have to make the dreams of the architect, which are always bringing new systems and new materials, they have to make them safe. And given that we know so little about fire, the role of the fire engineer is quite difficult. However, this is good in a way because it brings dynamism and excitement to fire safety engineering. It's a field that is always being challenged by the need of new ways of thinking and new solutions. However, also means that new materials and new systems are arriving and are at a rate at which we cannot catch up in terms of understanding what is the safety, flammability, and the fire behavior of these composites. For example, facade, new type of facade build in the buildings or timber buildings are examples. The engineer, that fire engineer that has been given the task to design the protection of a building would typically consider a set of layers. It would not just consider one way of protecting the building, it will look for redundancy. And when you look into all the tools, all the layers that are available for the engineer, you can put this in different ways. I like the way Professor Ducal Drysdale put them forward, which can be reduced to 6 of them. The first one, the single most important layer of protection is prevention, which means do not let the fire happen to begin with. I'm talking about technical or engineering prevention, not just say to the kids, don't play with matches. That is indeed prevention, but I mean technical prevention in the terms that the materials that are in the building should not be in excess of flammability, and the ignition sources, accidental or otherwise, that are in the building should not be in excess of strength. Because if you have a very strong ignition source next to a material that is very flammable, you will have failed at prevention. Whereas if you are only allowing ignition sources that are weak or rarely happening, and materials that are of low flammability, you will be succeeding at prevention. Once the layer of prevention is breached and there is a fire, has been a failure already for the protection of this asset, the second layer kicks in, which is absolutely essential. The fastest we can detect the fire, the better. And then how we communicate that detection as an alarm typically means to evacuate the room of origin, evacuate the story of origin, maybe evacuate the building, or kicking the fire strategy. Because the third layer is evacuation, to allow the people to be able to escape the site of the fire as soon as possible, and allowing everybody to be able to reach a safe place. That's a very important layer in fire protection evacuation. The fourth layer is compartmenting, which is don't allow the fire to move, the fire or the smoke to move to a different room. So it's okay that well, it's not okay. You have failed at preventing the fire. One room has a fire, but don't let the fire and the smoke go into different places. Compartmentation is an important layer. And the fifth layer is suppression. Suppression is to try to stop the fire or to reduce its size until more help arrives. This could be sprinklers, for example, that will belong to the suppression layer, or the fire brigades themselves are the suppression layer. Fire brigades are a very important element in fire protection. They are not a layer because they are present in very much all layers. The fire brigades has roles in every single one of the layers, in particular the evacuation and the suppression layers. And the last layer, which is probably the least known to people, is that the building or the structure should not collapse while there is still people or firefighters inside. It's debatable with authorities and the owners of the building if it's okay for the building to collapse when no one is inside or nearby, and that's controversial, but it's definitely not allowed to the structure to fail when there is still people inside. So these are the 6 layers. Some other layers some of you might be thinking about can be in a way rearranged into this, and I'm happy to take questions if you have some reviews. Now, there is this exercise that I've been doing with myself for a while that I would like to share with you. I've been thinking of the safest structures from fire that I can think of. Human-made structures that are the safest from fire, where actual people live in. I'm not thinking of a science fiction. I'm not thinking of of something that was seen once. These are three structures which I've seen myself and I've experienced. And let's see how each of the layers of fire protection work in each of them. You might be thinking, what do you think could be these three layers? So these three structures. So the first one that I saw is the igloo. The igloo is made of ice. You can definitely live inside, and it's much warmer inside than outside. Not warm enough from me inside, but it's still warmer than outside. It's protecting you from the wind, and actually it's a house for the people who live in very cold environments. Is very safe. It's one of the safest structures that I can think of because the prevention layer is very effective in terms that it's so cold that fire actually, the fire doesn't want to be initiated. The ignition sources fail at igniting the fuel. So you could actually have a very flammable element inside the glue, but the ignition source will have to be extremely powerful to overcome the cold conditions. And you can still install, if you would like to, detection, and obviously you will have evacuation because it's a small environment. Compartmentation, you always have the glue separated from each other. People will not be in a fire. A fire and a glue will not pass to the other one. Suppression will be natural as the ice melts. And structural resistance, is the glue will collapse, but it will not collapse when someone is inside because it's so small, it's easy to evacuate. The other structure that I saw that is very safe is a bunker. Military structure or civil structure to protect from a military event. They rely on prevention in the sense of that they don't allow materials that are flammable without a reason. Obviously, if they were to have ammunition, that is a very flammable material. The detection is rudimentary, but there is detection. And obviously, there is a very big role for evacuation. Compartmentation is absolutely essential in a bunker. Suppression, that would not be typical. You will not see sprinklers in a bunker, but there might be extinguishers. And structural resistance is the strength. The last layer is the strength of the bunker. Is that you might be losing parts of the bunker, but you will not be losing the rest of the bunker, and they will not be collapsed. And the last structure that I thought is very safe on fire is a spacecraft. In particular, a spacecraft as they are done by NASA and Russia. Because there have been fires in space. The spacecraft has oxygen because astronauts need to breathe. And there are a lot of ignition sources, all the electronics, and there are a lot of polymers, and the polymers are flammable. So it is definitely possible, and it has happened that there are fires, yet the spacecraft are very safe because they cannot call the firefighters and they cannot evacuate. So already layer number 3, evacuation as a whole is not possible. And suppression is very controversial because you might be damaging how do you perform in the module that is on fire. But there is a lot of prevention. NASA pays a lot of attention to the materials that go into a spacecraft. They don't put any material. They have very high standards for flammability, and they look into the ignition sources to avoid them. Detection is very important. Spacecraft evacuation, you can evacuate the modules, but you cannot evacuate easily the whole of the structure. Imagine, for example, that there's a spacecraft that is going to Mars. It takes 1 year to go, 2 years to come back, something like this. About 3 years in total. You can evacuate the module, but you cannot evacuate the space. So coming back to Earth will be tremendously complicated for the crew. Suppression is a big layer in a spacecraft, and structural resistance is that the fact that it's not collapse and it should not be destroyed as a vehicle. So just these 3 examples for you to think about how to reach safety and houses. And then in reality, what we have is we have our homes and our buildings where we work and where we live and where we do things. And they don't look like igloos. They're much more comfortable. They're not like bunkers. They're much more beautiful. And they're not like spacecraft. They're much more normal. They're not as fancy and high tech. And that's what fire engineers work. They don't work on igloos, bunkers, or spacecraft. They work in buildings where people want to live and need to live. In this is when fire science comes in. So fire science, which is the study of unwanted combustion, of fires that are accidental and are unwanted. And its aim is to create new knowledge, to discover something that we, as a human collective, we didn't know before. And And then that's not enough itself for our science to come up with new knowledge and keeping it for ourselves. That's nice, but that's only half of the work. The other half is then to share this knowledge, in particular to reach out to industry, to engineers, and to practitioners, which is to transfer this knowledge to society, such that the engineers and the practitioners can do something new, add protection, do things better or faster and safer, and protect us from the fire, and protecting the life, the property, and the environment that we love dearly. Just a note about this: fire science's origins as a science are dark. Fire science as a branch of science was literally created during the Second World War, and it was not to stop unwanted combustion. It was actually to create incendiary bombs, particularly good for the countries that were being attacked. It could be Germany, Japan, or the UK. And every big nation was actually doing fire research to develop incendiary bombs that were particularly effective at burning the houses of the enemy. So a very sad beginning. But then after the war, there was a very clear signal, particularly in the United States and the UK, that knowledge that had been collected so fast during the war now was going to be used for the good, for peacetime fire research needs, and to stop the fires that were damaging so much the cities. Now, take into account that we've been dealing with fire for a very long time. Wildfires have been burning on Earth before we became a species. The beginning of it, we humans, our ancestors, were fleeing fire in absolute fright, just as you can see many mammals are fleeing fire when they see a fire in the forest. But at some point, they think that it was about 1.5 million years ago, humans, or some humans, they stopped fleeing and they went back to the fire, to the wildfire. They started to look at it. Probably as a future scientist, maybe play with it, explore, and this led, fast forward 1.5 million years, to one of the greatest, no, actually, to the greatest single discovery in human history. This is not me saying it, although I think so. This was Professor Asimov when he reviewed and his encyclopedia, all the knowledge of humanity, and he realized, he stops at fire and says, what a discovery. It led to the way we change cooking, heating, science, industry was created, weapons were created, management of the forest was created, and also the combustion engine. So when in combustion, we tend to say that although engineers develop understanding of combustion, so it helps us to develop power, electricity, transport, synthesis of materials, also fire is an evil element in our houses. So fire is a good servant, but fire is a bad master. That's a motto from Finland that we like a lot. So fire can be good, fire can be bad. This is a slide that I use when I teach fire safety to kids, to young adults. And that to tell them that not all fires are bad. So if you see this fire over here, this is a facade fire nearby where we live in Chiswick, Travel Lodge, the facade burned, that's a bad fire. Everybody would agree. This one over here, ugly looking electric socket that has been overloaded and has melted and partially burned and charred, that's a really bad fire, and that's a close call to the people that were living nearby. But now, today is not particularly sunny in London, but we are in the summer and it was sunny a few days ago. A barbecue is a very nice event. Or cooking with a naked flame. That's a good fire. That's definitely fire, but it's a good fire. Or for example, our boilers that are giving us hot water and heating during the summer are definitely good fires. So it's relatively easy to identify if it's a good fire or bad fire when it happens in our buildings. But what do we do when it happens in our forest? So this is a photo that I literally don't know where it's, which forest we are seeing, but it's obviously that it's burning the forest. And the question is this a good fire or a bad fire? And some of you will be saying, it's obviously a bad fire. The great majority of people think it's a bad fire because fires are only in the media when they cause damage, when they produce an emergency, when they kill people, they destroy a forest that was dirty, or when it produces emissions. So then people think that all wildfires are bad. But that actually is not true. This could have been a good fire. The reason why they could be a good fire is because we humans discover wildfires. We did not invent them, which means that nature has a role for wildfires. Nature allows wildfires to happen for a reason, and that reason actually allows the planet and life as we know it. It happens that planet Earth, the land surface of planet Earth is very flammable. Plants are very flammable. There is not one single plant that is not flammable. It's just levels of flammability. And the atmosphere is rich in oxygen in a particular value of 21% in volume. That makes flames quite strong. If it were to be lower, 15%, flames would actually not be able to be sustained on Earth, but it's 23. So nature has a role for fire. In particular, fire is known to close the atmospheric oxygen cycle or the carbon cycle, and actually has very important roles in regulating the climate. And fire has shaped most of the ecosystems that are known on Earth. The only continent that doesn't have a role for fire as we speak now is Antarctica. But actually in the past, Antarctica also had fires. So fire, actually most fires, historically speaking, are good, most wildfires. It's just that now that we are seeing fires that are not good, and we need to identify why they're not good. So if you remember the layers of protection that I mentioned to you that come from fire engineering and were developed of how to protect a building, we can also develop these layers to protect the forest. And again, the single most important one would be prevention. Do not let the fire to happen, especially if it's accidental, which means nature doesn't have a role for it. So you should try to avoid that prevention. Although if you prevent all fires, then you will be also preventing the good fires. So you have to be really smart with wildfires, and you really need to know which are the fires that nature has a role for and which ones will be damaging that role for nature. In order for you to take a decision, if this is a good or a bad fire, you need to detect it. Otherwise, you cannot take the decision. So the second layer is as important. Third layer is very important, is this being a good fire or a bad fire from the point of view of nature. If humans are in the way of a fire, then it becomes an emergency, and then you have to act. There is no way to think about, there is no role for thinking. If there is people at danger, or there is property in danger, then this fire has to be stopped, at least locally, has to be stopped. And you might have to evacuate, especially what is called the wild urban interface, WUI, which is when people, houses, towns, the fringes of a city start to interact with the forest. And when the fire arrives there, you have to protect them. The fourth one will be compartmentation, which in forest science is called containment. Fire breaks, you will be familiar with fire breaks. You will be familiar with the role of rivers and the role of highways, for example, in not allowing sometimes the fire to go across them. That's the same concept of compartmentation of the fire doors that we have in the UK. The very similar will be fire breaks and rivers. The fifth one will be suppression, which is the darling of forest fires. This is the one that is always in the news when air tankers in particular, these beautiful large airplanes full of water are dropping the water on the fire. The images are incredible, and news people know that, and they use them all the time. But that's just one of the 6 layers that you can invoke for suppression of a fire. And the last layer is actually doesn't really rely on fire science, is actually more ecology, is to not to allow the ecosystem that has burned to collapse. So it's resilience, it's resistance to the fire, such that it can grow back again after the fire. And the 6th layer is very important, because if it truly was a natural fire, a naturally good fire, then it will be good for the forest, and the forest will be able to come back in a healthier state than what it was at the time of the fire. Now, in the news, you all are thinking about, there are always, and any time of my career that I've been giving a talk on fire, there has been a fire in the news, a fire in a building or in a forest. So as we speak right now, you are hearing about 2 types of fires. wildfires. The one is in the Amazon. It is true that there is a very large number of fires in the Amazon. Every single year, there is a lot of fires in the Amazon, and it's very difficult for fire scientists, ecologists, to decide if truly the number is going up or down in years, or what are the causes for this. I'll tell you a little bit about why this is difficult. I go and show this to you in the country that has the best data possible. This is the United States. The United States has an amazing, incredible data set on wildfires, much better than the one in the UK, because in the UK we have very little wildfires. So in the UK, in the US, they've been collecting data, for example, or firefighting cost. How much does the government has to pay to the fire brigades to extinguish wildfires? And you can see the plot there since 1985 going to 2015. That is a very clear signal is growing up. They are putting billions into suppressing, which is one of the layers only of these fires. So in the US in particular, the problem with bad fires is growing. If you look into why it's growing, you have this data from the same years in the US. You have in blue, you have the number of fires in thousands. You can see that that's steady. So actually the US doesn't have more wildfires. It has the same number up and down that it had before. What they have is bigger fires. Look, the data in black. That's the area that has been burned in thousands of kilometers square. And what you can say is that there is a massive signal increase, that they are actually having bigger fires. So the more they suppress, the bigger the fires they have. And this has been a puzzling outcome of US policy, and which has only been observed in the US, also because it's the best data set. And the conclusion of the scientists has been for the many last decades that the problem is the concept of fire exclusion. In the US, they've been fighting so many fires, assuming that all wildfires were bad, that they allow the fuel to build up. So pretty much their forests were not healthy anymore. They were not natural forests. They were altered forests because fire had been completely excluded. Also, the good fires had been excluded. And that meant that any opportunity for an accidental fire, the fires would become mega fires, absolutely humongous fires that actually lead to a further deterioration of the health of the forest. So it's a very bad situation that they are in the United States, where the more they fight fires, the worse they get, and the worse the quality of their forest. That's something very specific to the US, because the fire exclusion and their muscle to extinguish fires is unmatched in the rest of the world. Only maybe a little bit close to it will be the south of Europe or Australia, but still US has different proportion. This is an image of planet Earth with pixels where fires have happened. The reddish, the color, the more that pixel has burned, and the bluish, the less it has burned. And if it's white, it means that there is no data, which means there was no fire. And it's covering from 1997 to 2016. So the first thing that you can say is that fire happens pretty much everywhere on Earth, except if it's too cold, like in the poles, or if it's so hot that it's actually a desert and there is nothing to burn. Particularly, you will see that there is a lot of fires in the Amazon. Historically, there is a lot of fires in sub-Saharan Africa every single year. There is a lot of fires in the core here of Russia and the south of Russia, and there is a lot of fires in the north of Australia. Historically, you can see that it's a very fire-prone planet. The reasons why this situation is changing, and some regions of the world are going up in the number of fires, some other regions of the world are going down in the number of fires, some regions of the world are going up or down in the size of the fires, and some countries are going up or down in the damage to people or to the property that these fires are doing. The reasons are because of three changes, and this is very complex because these three changes are simultaneous and important. So the three changes explain trends in different places. First one is that land use is changing. So if you have land and you want to make it agricultural, then you have to deforest it, like it happens in the Amazon. And then you are making it, you're changing its flammability, and you might have to burn it to begin with. So, or you abandon a forest, not a forest, you abandon land that had been treated by the locals, and then it grows wild, and then its flammability will change. So changes of land use are one of the important changes to fire behavior going up or down. The other one is population movement. People going away from the forest or people arriving to the forest. Both of them actually have consequences in the flammability. People are themselves ignition sources, but also people learn how to live in the forest and how to take care of it. And the two movements can increase or decrease fire. And the third one, which is a modern one, is of the last decades only, is climate change. The fact that the climate is changing and the ecosystems are being altered and the conditions of temperature and moisture and wind are changing. That means that our fires are also changing. And it's really difficult to know, for example, how much of land use change or population movement or climate change is in the United States, because you have this fire exclusion decision, and it's very difficult. We have to go to other places to see this. So we look into Australia, we go into the Amazon. When we go into the Amazon, we think that it has to do a lot with climate change or like land use changes. So the two changes number one and change number three are very important in the Amazon. And it's not clear for us scientists to identify which of the two is the most important one. They are masked on top of each other. But there is one case which is very interesting. The Arctic. There is an unprecedented number, size, and activity of wildfires in the Arctic. In the Arctic, all the Arctic. I'm talking about Siberia, I'm talking about Greenland, I'm talking about Alaska and Canada. Massive, unprecedented increase of wildfire activity over the last decade. And in this case, actually, it's much easier to identify the three changes because that's not because of land use. There is very little interest in changing the land use of the Arctic. Pretty much there is no human use of land over there, is wild. There is no problem with population movement because all there is people living in the Arctic. There's very little amounts and it's changing so slowly that actually is negligible effect that it has on the Arctic. So the only signal that is meaningfully present in Arctic fires is climate change. So for me, it's very obvious that the unprecedented behavior of wildfires that we're seeing in the Arctic is a very strong signal of climate change. Whereas it's more difficult to say this in Australia, in the Mediterranean, in the United States, in the Amazon, because all these three changes are masked with each other, but it becomes much clearer in the Arctic. So with this, I would like to finish just to say that fire is this greatest discovery of humankind, and is both a natural and anthropogenic hazard. Bad fires are a concern, has been always a concern because of the toll that it has on lives, economy, and ecosystems. That fire engineers and fire practitioners are here to protect people, the property, and the environment, and that there is such a thing as good wildfires. Hopefully it will be something that you've learned today for many of you, and that a better understanding of fire enables to understand when the good fires are happening or not, and the innovation and the development of new technologies. There is much to do and to make this world safer and to differentiate between bad fires and good fires, and all your help will be most welcome. And now I'm happy to answer your questions. I just want to say thank you to my group of researchers here at Imperial College, and obviously my sponsors, our sponsors. Without them, nothing of the work that I've been doing would have been possible. Thank you very much.
Thank you very much, Guillermo. I think we occasionally do a round of applause, but let's leave that for the unmuting at the end. So what I'd like to do now is to go through the questions as they come through in the chat column. And we've had two to start with. One is from Ian. The wildfire size pattern in the US is clear. You alluded to the cause during your talk, but do you have a fuller answer as to why the size is increasing?
Yeah. So the scientists for the last decades, it's not even recent research. They are quite certain now that the reason why the size of the fires in the US are going up is because of this fire exclusion technique in the US. Fire exclusion technique, maybe I haven't explained it well, is that since 1910, the US Forest Service has to stop every single fire burning in the forest, every single one, small or large, anywhere in the country. And they became really, really good at doing this. And they were stopping the good fires as well. And they were building up fuel in the forest such that their forest became extremely, actually as we speak, are extremely flammable. And then any fire, now it's not a small, now any fire becomes quite quickly a mega fire, a big fire that they cannot stop.
So I'm familiar from growing up in the north and seeing the commercial forests in the Peak District with the idea of fire breaks. Was that not employed in the States?
Yeah. They have significant and very large fire breaks, but that's not enough. Especially because the problem it is with fire breaks is that you have to decide a width of the fire break. And it's key. If you make it very wide, you are destroying a big land of forest. But if you make it not wide enough, the fire, in particular the embers, can actually jump over the fire break. And then the fire break actually has just slowed down the fire instead of stopping it. So mega fires, the largest type of fires, the one that actually we worry about the most, cannot really be stopped by a fire break.
Okay. Sort of related to that, and perhaps your comments as well on the polar fires. What is the temperature that triggers a natural wildfire?
Oh, that's an awesome question. I can say it's so good that as we speak, we are actually conducting experiments on this. I have a grant from the European Union to look into this same question. So I can say that we don't know yet. We don't know yet in Hayes Lab, we don't know yet in the world, but it is clear that as the temperature of the land or the soil or the vegetation or the air goes down, that the fire activity is decreased. The question is, what's the threshold in temperature such that it stops all fire activity? And we have not been able to find it, but we know that when the winter arrives to the Arctic and it freezes absolutely everything, and there is even a cover of snow, most wildfire activity disappears until the spring arrives, with the exception of what are called now zombie fires or holdover fires, which are smoldering under the snow. And they wait very patiently, very cruelly. They wait, burning very slowly, insulated under the snow for the spring. And then when the spring arrives, they actually flare up and they cause a much bigger fire because it doesn't have to grow from zero.
Okay, I've just got a voice in my ear from the TV production suite at Friends event, which is, could I ask Guillermo to stop his screen share? Obviously, this conversation will have to be edited out to the final version that wins the BAFTA award. So, thank you very much. Another question from Marta: How has fire engineering changed after Grenfell Tower? Is ACP still used in certain contexts?
Good question. Very little has changed in fire safety engineering since Grenfell Tower in terms of how we do the buildings, how I don't do buildings, how fire engineers do buildings, but everybody's expecting big changes. We just don't know in which direction. The government is giving signals in one specific direction. The community itself would like to see signals in a different direction. In reality, there is a lot of talking and there is very little doing, which is a particularly uncomfortable situation to be, because we would like to see the citizens seeing action and solutions being put into place. But there is a lot of discussions going on. Every single member of a fire community has been involved in discussions about this, not only in the UK, but also, for example, in Australia or around the world. Everybody's looking into what happens in the UK. About ACP, which stands for aluminum composite panels, I don't think anyone will dare to use them now because been shown to be a material that fire engineers were not understanding well enough. Now, because of Grenfell, at least that material is understood to be in excess of flammability. So no one no one that reads and is aware of the news will be using it. And also, whoever wants to use ACP now will have a almost impossible chance to get it approved because everybody's paying attention to this. Our worry is other materials that we haven't learned yet about their flammability, and there are fancy new materials with big promises, but we don't want to be caught again by a material that we didn't understand well enough, and it led to something like this.
Okay, thanks very much. Question from Rod. What can we do to limit fires in the polar north, as these are a mechanism for pushing CO2 into the atmosphere?
Very little. This is wilderness at its maximum extreme. If fires are happening there, it's because planet Earth wants fires over there, and it's really, really difficult to stop them. Mostly because no one is interested in stopping them. For example, fires are happening in Siberia now. The government was not even aware that there were fires happening there. No one was there to see them or to be bothered by them. It was the satellites, mostly in international consortia of satellites, that were seeing the fire activity, and they started to raise the awareness of the activity. And then, for example, Greenland would be a case. The government of Greenland in Denmark was so bothered by people watching these wildfires happening in Greenland through the satellite that they decided to act. So it is almost like the satellite and the community became the detector. We said there is a fire and this is not normal. So at the end, they sent fire brigades from Denmark to Greenland. And actually, it was very easy to stop. They stopped the fire in 3 days. It was a big fire, but it was really easy to stop. So apparently these Arctic fires are very large and unusual, but apparently they are very easy to stop with conventional ways of stopping, but very rarely are stopped. Only Canadians and Alaska in the US are interested in stopping these fires.
Okay. Great answer, thanks very much. Let's see. Yes, so that's more a comment from Ian there. Right, and from Helen, is it possible to compile a wildfire hazard map to stop people living in high-risk fire engines?
It's definitely possible, and the maps exist, and the maps are freely available, and it's actually many people have been doing these maps, yet people decide to leave for reasons that are not the maps. For example, the case of the difficulty that we are discussing is what happens in California as we speak. This year they had an easy year, but in the last 3 or 4 years, California has these massive wildfires burning their wild urban interface where people live. And if you look into historical maps, these houses were in places where previous fires had happened, which means that these people are in a way accepting the risk of their houses being burned by fire. And the answer to that question is the maps exist, and I would love social scientists to help us to pass the message better and to understand why action is not taking place the way it should, maybe.
Okay. I infer from the comment that Peter Michaels put, he said, I can add something to this conversation. I think you might have some regional expertise. Would you like to come on voice, Peter, to ask the question?
I am on voice. Yes, hello.
Oh, good.
Thank you for a very interesting analysis there. And my question really is that I believe your research has been going a relatively short space of time, and it will at some stage reach the practical fireman on the grounds. At the moment, I guess there is probably a bit of a gap that you're trying to fill in. And the contribution I was going to make was regarding North California and other places where we grow grapes on mountainsides and have very personal experience of wildfires of hundreds of thousands of acres that have been burning We've always had fire. Every year we've been there for 30 years, there's been fire. In Northern California, it's endemic. Where you grow grapes, it's dry, and there is a lot of wild countryside to burn. Couple of interesting things though. Some of the starting points of the fires were analyzed, and they found that arson was very much to blame. And in fact, they caught 2 or 3 of the arsonists. And bearing in mind how much damage was done, I suspect that if they aren't in jail, they probably had a bullet in them. And the other reason was slightly different from that. Accompanying the fire, there were very high winds, circular winds, that caused the fir trees to sway into the power lines, break the power lines. The power lines were supposed to trip. The PG&E trip didn't work. And so these fizzing 33 kV lines were fizzing around on the ground and setting the brush alight. And one evening there were 200 separate fires started by this process. The claims against PG&E for that damage has put them into Chapter 11, which they may never exit. But the bit of good news about it is that the vineyards turned out to be very difficult to set alight. And one of the best places that you can build a house is in the middle of a vineyard. And you can be happy looking at it and drinking it forever and ever.
It's no, thank you, Peter, for the question. It is an important question. So you refer to the big fires are happening in California, and the fact that they are in the news, and actually there are court cases, and there is a lot of investigations on this. My worry about all this is there is an undue importance that is given to the ignition source in these fires. The ignition source, or the arsonist, or the accident, or the reason, the technical reason why the fire started is very important, but an ignition source cannot lead to a mega fire alone. Something else, the ignition source and something else has to lead to the mega fire. An ignition source per se just leads to a fire, as California has been having for the last multiple thousands of years. So something else is happening that an ignition source now is able to lead to this devastation that we are seeing in California. And my take is that the 3 changes that I'd mentioned are playing a role, in the sense that there is population movements, the wildfire interface is growing, and that brings ignition sources and brings more properties to be protected. There is climate change to be discussed, and if that is bringing stronger winds or not, and it's bringing drier fuels or not. And it's not clear for us as we speak. The California problem at the end is recent. Science didn't have time, as you were alluding, Peter, to do their studies and communicate them. As we speak, they are ongoing. I can tell you California is such a powerful research center, right? I graduated in California for University of California, Berkeley. They have Berkeley, they have Caltech, they have Stanford, have Irvine. I mean, they have these amazing research institutions. And together, they don't have more than 1 or 2 fire scientists. Whereas the bill that now the state has to pay is billions, if not trillions, and the damage to the reputation is insane, massive. So yeah, there could be more fire science, and then that will lead to a better protection of the state and of the rest of the world. And there is a lot of things that can be done, and there are a lot of things that the state decided not to do.
Tell us about them, if you will. Do tell me.
I love California, beautiful place, by the way. I don't mind to go back, and I have a lot of friends and a lot of scientists there. And I know there are struggles that they had to be here. And now after the catastrophe, at least they are listened to. And it's a pity that fire science has to wait for a catastrophe to be listened at. And while there is no catastrophe, there is no interest in building resilience or understanding towards avoiding the catastrophe.
Okay, thanks for you two have just reminded me that when we lived in Australia, arson was the cause of one fire that was in the area around Perth, and the person who started it, the arsonist was a volunteer firefighter. So I don't know whether he was looking for some business for himself, but yeah, people go into firefighting for a number of reasons, shall we say.
So, John, because that could be a question itself. So ignition sources are they can be very different.
Mm-hmm. Okay.
Are human ignition sources, the cigarettes, all these things. And we also have the natural fires, which are caused by nature itself. Like lightning strike is the most popular one by nature, so to speak. And also self-heating, which is the fact that a fuel that is accumulated in a pile left in a relatively warm place can itself develop a hotspot in the center that will develop a fire. So humans, we alter the landscape by bringing ignition sources, but nature does it as well.
And the name of your haze lab was with reference to the hazes that blanketed Southeast Asia in the last decade. So these are natural fires that start in forests.
It is. We named the group horrible regional event, where a cloud of smoke stays attached to the ground instead of being high up and being carried away. That actually the smoke stays in the land for weeks and months, where people live and people have to do their living. So the health and economic consequences of haze are massive. And Southeast Asia, because of peat fires in Indonesia and Malaysia, is particularly badly hit by haze. And this is about a third of our research that I haven't discussed today, that it goes into helping to understand and to stop haze.
Mm-hmm. Going back to the polar fires, Ian's curious about zombie fires. How long can a zombie fire exist? Is it an ancient fire? Is it just one season, or is it several years?
That's a very good question. So the ones that we have followed scientifically, they only last for one season. Maybe they start at the end of the summer. They go underground, but they don't die off. And they survive the winter under the snow cover in a very interesting play of heat transfer and oxygen arrival. So the fire is smoldering, it's not flaming, underground. And it has just enough oxygen to be burning. But the snow actually is insulating the heat losses. So it's a very different type of fire. And then the spring arrives and the fire comes back. We haven't seen this being repeated over other seasons, although, for example, but not Arctic fires, but fires in the delta of the Congo River has been seen to always be a fire in the same place every single end of spring. And chances are very high that there is a zombie fire that is literally living in the ecosystem deep underground, and it just comes out every single time. And also talking about these coal fires, which is when a seam of coal has been burning for hundreds and hundreds of years is actually known. The oldest continuously fire known to humanity is actually in Australia, not far from Sydney. It's called the Fire Mountain, and it has been burning for the last, at least for the last 6,000 years, at least 6,000 years, maybe 500,000 years, continuously. And it's not a flaming fire; it's a smoldering fire that is burning underground, where the coal is always finding enough oxygen to keep burning.
Okay, thank you for that. We've got, I think we'll take this as one last question. I've got another one, but just for curiosity, what is the difference between the fire caused by electricity and a natural fire? Is there a difference in the fire temperature and the color? This is from Namita Sahu, who thanks you for the talk as well.
So the ignition source is this very specific event that initiates combustion and fire. And shortly after the ignition has succeeded at creating a fire, the fire has no memory of what caused it. The fire has no memory of what initiated it. natural fires and arson fires can behave very, very similar. And definitely within meters or within minutes, it's very difficult to see any difference in them. You will have to look into the pattern of ignition. An arsonist typically doesn't do it once. An arsonist might be trying to put a fire in several places, and then you can see that partner, whereas nature has a tendency to just create one big ignition source here and another one 20 kilometers on the other side.
Okay, if I may, just one last question. Additive manufacturing is going into vogue and creates very fine metal dusts. And I note that it's also used on the space station, International Space Station. What research has been done into additive manufacturing fire potential?
That I know in my community, which is the fire science community, nothing. The first person that ever mentioned this as a concern was you, John. And when you told me, I was not surprised, because one big topic of research in fire science is the flammability of dust. So dust of any material that is flammable always brings the worst in terms of combustion behavior, to the point that actually you can have a dust explosion. You take wood, which burns very well in the forest, you make dust out of it, you make saw, you make it airborne, and you can have not only a big flame or a fireball, you might actually have an explosion, a proper chemical explosion. So dust always exacerbates, increases the combustion behavior of the fuel. So I'm not surprised. Metals can burn. Not many people know this, but a metal that is made of dust can actually burn before the oxidated layer stops the fire. So metal dust can actually burn, deflagrate, and explode. So it didn't cross my mind until you mentioned it, John, that additive manufacturing requires you having this dust store, and then if this dust accidentally becomes airborne, you might have a big fire problem.
Okay, thank you. Well, we had Mac Lau raise a hand. Is he going to type, or is she going to type in the chat box? We've got 41 participants. Maybe can unmute. No? Okay, maybe it was just to test the function. So if we're all unmuted, could we give a round of applause to Guillermo for his excellent talk, and thanks very much for spending your afternoon with us, and look forward to catching up with you soon.
Thank you very much.
I'll hand back to Phil.
This is my first virtual applause. Thank you.
Very good. There'll be more.
Okay. Thanks, Guillermo, and for John, and I'll close the meeting, and we look forward to welcoming you people, friends, again in 28th of August. We have Will Nottenbelt, Director of the Cryptocurrency Research Institute at Imperial College, talking about cryptocurrency alchemy. So that's available on our website, and we look forward to welcoming you again.